Okay, let's look at a few examples of Green's theorem. And I'm also going to cover a couple of things that may not have been covered in great detail in class. So let's just give these a look. So here we want to evaluate this line integral, and we're going around the circle of radius 2 centered at the origin. Now, for this to make sense, this thing has to be oriented like this. Okay, well, let's just see what happens. In class, we have been calling this m of xy, and we've been calling this n of xy. So if we assume this orientation, then that's going to lead to Green's theorem. So we'll have the double integral over the region R, which is the circle. Okay, so now please understand, in the line integral, we're walking around the boundary of this. And here we're looking at the interior. So for Green's theorem, we need to take the partial of this, the second thing, as I've got it written. We need to take the partial of this with respect to x, and that's going to give us a 5. That's nice. Minus now, we want the partial of this with respect to y. So we took the derivative of n with respect to x and got a 5. And now we want to subtract from that the derivative of m with respect to y. And that gives us a 2. So look what happens here. We can take the 3 and factor out. Now, the limits don't really matter, do they? Because this is going to be the area of that region. So this is going to be 3 times pi times the radius squared. Now the radius squared, that would be 2 squared. So we get a 12 pi. As pretty as you please, and we didn't have to integrate anything. That's nice. Okay, so everyone see why that's going to work, because this double integral, see this double integral, since that's a 1, this represents the area of the region. This is the area. And I know that the area is pi times 2 squared because it's a circle of radius 2. Okay, so we want to evaluate this line integral. And the boundary is going to be a triangle. Let's make sure we get this right now. The boundary is going to be a triangle. And we begin at 2, 0. We go up to 2, 2. So is that right now? We start here, go this way. And then we go to 0, 2. And then back to 2, 0. And notice that the orientation is correct. The region R would be on your left. Your left hand would be over the region R if you're walking along that boundary. So Green's theorem has this to say, doesn't it? It's a double integral over the region R. Now we want to take the derivative of this thing. Careful now, we want to take the derivative of this with respect to x. So what is going to be the partial with respect to x of x plus y quantity squared? Well, it's just a chain rule problem. This would be 2 times x plus y times then the derivative of x, which is just 1. So this is going to be 2 times x plus y. Minus then, we want to differentiate the first term, that's our m, with respect to y. You always differentiate with respect to the variable that's different than the differential. This is dx, so we take the derivative with respect to y. This was dy, so we take the derivative with respect to x. So this is going to be minus a 2y. Well, let's look at what happens. You see what's going to happen. This is going to be 2x plus 2y minus 2y dA. Okay, so we end up then with the double integral over the region of 2x differential dA. Okay, now you get to choose. What do you want to do for the order of integration? Well, clearly this line is x equals 2. This is y equals 2. So what's going to be the equation of this? Well, the slope is going to be down 2 and over 2, so the slope is 1. So that's going to be y equals minus x, and then it has a y-intercept of 2. So that's going to be y equals negative x plus 2. So I think I will integrate this with respect to x and then with respect to y. You could go either way. So I like to do the easy one. Y then is going to go from 0 to 2, and x is going to go from 0 to the equation. I'm sorry, that's not right, is it? X is going to go from the line to 2. It's going to go this way. So this lower limit's not going to be 0. The lower limit's going to be 2 minus x. So x is going to go from 2 minus x. X is going to go from 2 minus x. That's not right either. Let's think about this. If I'm going to go this way, I have to change the curve to x equals 2 minus y, don't I? Swap these two. So let's get this right. X is going to go from the line, and the line has equation 2 minus y, and then x stops at x equals 2. Oh my goodness. Okay, so let's look at the first integral. That's going to be the integral of 2 minus y to 2x dx. Well, that's just going to be an x squared, of course, evaluated from 2 minus y up to 2. Now plugging in, we get 2 squared, which is 4, minus then 2 minus y squared. Now we could leave it like that, but I think you can kind of sneak a look here at what's going to happen. This is going to be 4 minus. Now when we square this, we get 4 minus 4y plus y squared. So this ends up with a 4 minus 4. So we get 4y minus y squared. And now the second integral, to finish the problem, we're going to integrate from y equals 0 to 2, 4y minus y squared dy. Integrating that gives us a 2y squared minus a 1/3 y cubed. From 0 to 2, plugging in 2, we get an 8 minus 8/3, which is just going to be 24 minus 8 is 16/3. That limit there almost got me. I'm integrating with respect to x, so x must go like this. How does x change? X goes from this line, so I have to take that line and solve it for x. That almost got me, didn't it? Evaluate this line integral where C is the boundary of the region R between the quarter circles of radius 1 and 2 in quadrant 1 and the x and y axes. So I've got to make sure this thing is oriented this way. Okay, now 1, 2, and 1, and 2, x-axis, y-axis. Well, let's see now. Green's theorem says we're going to integrate over the region. Now I want to take the dy term, and I want to take the partial with respect to x. So that gives me 6x. Minus then, I want to differentiate this with respect to y. I get 0. Okay, now what's going to happen here? How are we going to do this? Well, this kind of region begs us to switch to polar. Okay, so I'm gonna change to polar coordinates. I either do that, or I'm going to have in the limits of the problem some square roots, and I'd personally rather not do that. So I'm going to get a 6. Now in polar coordinates, x is r cosine theta. And then we know from the Jacobian, we pick up an r, and then dr d theta. So then what are going to be the limits? Well, r is going to go from 1 to 2, and then theta would go from 0 to what? From 0 to pi over 2. Cool. So integral from 0 to pi over 2, integral from 1 to 2, and we'll get a 6r squared cosine theta, and then dr d theta. Okay, let's look at the first integral. Now in the first integral, we're integrating with respect to r. The cosine theta would be a constant with respect to that partial integral. So we're integrating from 1 to 2, 6r squared dr. When we integrate, completing the integration, we get r cubed over 3. So this would be a cosine theta. And what are we going to get? We're going to get r cubed over 3. The 3 and the 6 cancel, so this is 2r cubed, evaluated from 1 to 2. So this would be the cosine of theta, I guess. And then a 2 times 2 cubed is 8, 1 cubed is 1. So 8 minus 1 is 7, so we pick up a 14, and then cosine theta. So now the second integration. We'll have a 14, the integral from 0 to pi over 2, cosine theta d theta. Now the integral of cosine is sine, so this is going to be 14 sine theta, and evaluated from 0 to pi over 2, and I think you can see what's going to happen here. This is 14 sine of pi over 2, minus then the sine of 0. Well, of course, the sine of 0 is 0. The sine of pi over 2 is 1. So there it is, 14. Hard to believe you can be dealing with the region between two circles and end up with an integer answer. But that is, nonetheless, what happens. Cool. Nice problem. So we want to integrate this line integral. Well, C is the closed curve consisting of the graphs of y equals x squared, y equals 2x between 0, 0 and 2, 4. Well, we want this to happen. It has to be this path, doesn't it, for it to have a positive orientation. Okay? So then, what's Green's theorem going to say? Double integral of the region R. So we take the dy term and we take the derivative with respect to x, and that gives us 3x squared. Minus then, we want to differentiate this term, the dx term, we differentiate it with respect to y. And we get minus then a 5x. Okay. The next thing we have to decide is the order of integration. Doesn't really matter. This one is not hard either way. I don't have in the problem a boundary which is 0. It doesn't really matter. Let's integrate with respect to x first and see what happens. Well, I don't know. The curves are y equals, if I integrate with respect to x, then I'm going to be having a square root. I'm going to integrate with respect to y first. So y is going to go from the parabola up to the straight line. So let's set this up. This is going to be 3x squared minus 5x. And we're going to go dy dx this time. So x then goes from x equals 0 to x equals 2. What's y going to do? Y is going to go from the parabola, which is x squared. That's the low y. And then it's going to go up to 2x. I'm just going to do that to avoid square roots. So the first integration. X squared of 2x. 3x squared minus 5x dy. Well, I'm integrating with respect to y, so there, in this case, we're going to have the x quantity, 3x squared minus 5x, would be thought of as a constant. So that's going to give us a 3x squared minus 5x times a y, and that y is going to be evaluated from x squared to 2x. So now that's going to give us a 3x squared minus a 5x. Now I'm going to use square brackets just to separate them. Remember now, I'm plugging the limits in for y, so I'm going to get 2x minus x squared. Okay, so I'm just going to multiply the stuff together. So I'm going to get I guess I can use FOIL or whatever that's called. 6x cubed, right? Minus 10x squared. Minus 3x to the fourth. Plus 5x cubed. So that gives me what? That gives me a minus 3x to the fourth plus 11x cubed minus 10x squared. Written in descending powers of the variable. Now the second and last integral is going to be the integral of 0 to 2 of this stuff. And it's no big deal, is it? It's just a Calc 2 problem that everyone should be able to do. So minus 3/5 x to the fifth plus 11 over 4 x to the fourth minus 10/3 x cubed. Evaluated from 0 to 2. Now clearly 0 is not going to give us a contribution. So it's going to be whatever it is when we plug in 2. So this will be minus 3/5 times 2 to the fifth, which is 32, plus 11 divided by 4 times 2 to the 4th, which is 16, minus 10 thirds times 2 cubed, which is 8. So, okay, I'm going to try to make life as easy as I can. I'm going to factor an 8 out. So that's negative 3/5 times 4, plus 11 over 4 times 2, minus a 10 thirds. Well, look at what happened. Oh, that's a 3/5. I'm sorry, 3/5. 3/5. So that's going to give me a minus 12 over 5. Now look what happens here. That cancels. So that's going to be plus an 11 over 2, minus then a 10 over 3. Okay, let's do them two at a time. This will be 8. Now the common denominator of the first two would be 10. So that's going to be minus 24 plus 55. And then the minus 10 thirds, we'll just have to wait. Now I did that right. Negative 24 plus 55. So that's going to be 31. 31 over 10 minus 10 thirds. Okay, the common denominator is going to be 30. So this is going to be, we multiply by 3 over 3, so we get 93 minus 100. Now, did I do that right? 3 over 3, and then 10 over 10. So we get an 8 times a negative 7 over 30. And then we'll tidy this up. We have 4 here and 15 here. So minus a 28 over 15. That's not hard. It's just tedious. Hope I did that right. I think so. I don't see any terrible mistakes. Oh, my word. We want to evaluate this line integral where C is the cardioid, R equals 1 plus cosine theta. So we're going to integrate here from 0 to 2 pi. Now, when theta is 0, the cosine of 0 is 1, so R is 2 right here. Now, when theta is pi over 2, the cosine of pi over 2 is 0, so R is 1. So I would be right here. So I indeed do have the correct orientation that I need to invoke Green's theorem. As we walk around this boundary, the interior would be over our left hand. Our left hand would be over the region. So here's my region, R. Well, let's see what happens. Wow. So I'm going to take the derivative of this term with respect to x, and that gives me a y. Minus then the derivative of this term with respect to y. That gives me a 0. Let's see if I did that right now. I take the derivative of this with respect to x, that's y, minus then the derivative of this with respect to y, which is 0. That's what it is. Well, we're definitely switching to polar. Okay, so what's going to happen? Well, where we have the y, we're going to put r times sine theta. And then by the Jacobian, we pick up an r d theta. So r is going to go from r equals 0 out to the curve, 1 plus cosine theta. And then theta goes from 0 to 2 pi. Incidentally, this is called a cardioid. It's the only curve I use in Calc 2 when I teach polar coordinates. I just use cardioids primarily. Well, heaven help us. Let's see what happens. For the first integral, 0 to 1 plus cosine theta, r times r is r squared. So I'll have an r squared dr. And then the sine theta is a constant with respect to r. That's not too bad. So I pick up sine theta as a constant, and then this is going to be 1/3 r cubed, and that's going to be evaluated from 0 out to 1 plus the cosine theta. So what is going to happen? So I get sine theta over 3. Now I'll get no contribution from the 0, but it's just 0 cubed. So I end up with 1 plus the cosine of theta quantity cubed. Oh my word. Well, okay. Now the second integral, I'm going to take the 1/3 out, and I'm integrating from 0 to 2 pi, and then what I have to integrate is 1 plus cosine theta cubed sine theta d theta, and that's not bad, is it? That's just a straightforward substitution. So if we let u equal 1 plus cosine theta, that becomes 1/3 the integral of u cubed, right? Now du, derivative of 1 is 0. The derivative of cosine is minus sine theta, and then the differential d theta. So sine theta d theta is minus du. So I pick up a minus from the substitution, and look at that. Isn't that just amazing? We're integrating an expression in theta to a power, and we turn that thing into a polynomial. That is just slick. Now I'm going to change the variables. When the old variable theta was 0, the cosine of 0 is 1, so we get 1 plus 1 is 2. See? And look what's going to happen. Everyone see what's going to happen? When I let theta equal 2 pi, the cosine of 2 pi is 1. That, folks, is 0. Isn't that something? Isn't that so good? Isn't that good? I like that. That's a surprise. I did not see that coming.
That's pretty neat.
Okay.
That's pretty neat.
Well, let's see what else. There's just a couple of things I want to discuss here, tack on to the end of this little video. Now remember, in the hypothesis for Green's theorem, we have to have continuous partials for the vector function, but we have to be in a simply connected region, which means there's no holes. And you remember in class, I went through this, and while I was saying all this, I held my fingers up crossed, because we're going to cheat. What we're going to do is right here for this circle, see, this is not simply connected. Simply connected just means there's no holes in the region. So here's what I'm going to do. I'm going to come right over here and put an imaginary cut. So now look, I'm walking this way, right? This is a correct orientation. And then on this little bridge right here, on that little bridge, I'm going to walk this way. So I'm walking here. I'm going to walk this way, see? And I would have to walk this way because I want the interior to be on my left. See, imagine yourself up here walking. Now watch, I'm going to walk around here, and then I'm going to walk straight out the imaginary cut this way. So they're in effect going to cancel. And then guess what? I'm going to walk this way as normal. I'm going to come over here and I'm going to make a cut right here. And see, I'm going to come here and go this way. And then walk around this way. Go back this way. Walk back here to where I started. Now, what that in effect does is take and split the region, and it allows us to integrate everywhere, and in effect there's no more holes. See? So that's pretty cool. Now, when you work a problem, do you have to break the given curve up into a bunch of curves? No, because see this, when you walk this way, that's going to be the positive direction, negative direction. They cancel. Now, when I say negative direction, when you walk this way, that's considered positive. And then now when you go back out that way, that's the negative direction. So they cancel. So let's look at this little problem. See here, we've got a region. This is our region. I've got this set up here in this one. And everything is oriented correctly. So what I'm going to do is walk around. And I'm going to go right here. I choose to go right here. I'm going to go this way. Because when I'm walking this way, bum, 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 the region's on my left. When I get to here, I'm going to walk around this way. Come here, I'm going to walk back out this way, which would be the negative direction on that path, and then finish my trip. So I can now use Green's theorem on this. Okay, now, it's just like any other Green's theorem problem, and I think I'll just set this one up and we want to differentiate this with x. Well, look, that's a 1, so that's 0. That's ugly as all get out, but there's no x's. So we just get a 1 here. Minus then. Now, I want to differentiate this with respect to y. Well, that's 0. I'll get a 3x squared. And then plus a 3y squared. And I hope you can see what's going to happen now. We're going to switch this little deal over to polar. And we'll get 1 minus 3r squared. And we'll get an r d theta. R is going to go radius 1 to radius 2. So from 1 to 2. And then theta is 0 to 2 pi. Now, just a point here. It doesn't matter where you put this little cut. It doesn't matter at all. Okay. I think I'll just go ahead and work this because it's not going to be much to it. If we look at the first, we're going to get the integral from 1 to 2, and we're going to get an r minus 3r cubed dr. So that's going to be a 1/2 r squared, and then that's going to be minus 3/4, isn't it? 3/4 r to the 4th from 1 to 2. So what's that going to give us? Plugging in 2 squared is 4. Half of 4 is going to be a 2. Minus now plugging in 4. 2 to the 4th is 16. And then 3/4 of 16 is just 12. Minus then, plugging in a 1, we get 1/2 minus 3/4. So this is going to be minus 10 minus, now what's 1/2 minus 3/4? Well, 1/4 is 2 over 4, so we have 2 over 4 minus 3 over 4 is a negative 1/4, so it's 1/4. What is that? what's that going to be? Negative 39 over 4. So then second, we'll have a negative 39 over 4, the integral from 0 to 2 pi d theta. So that's a negative 39 over 4 times 2 pi. So a negative 39 pi over 2. So you can just make a little cut like that and then go ahead and use Green's theorem. Very, very cool. Very, very cool. Brief discussion. And then finally, now you remember one way we wrote line integrals was to write it as the vector function dotted with t ds. This is usually the way that the work is defined. So you've got a vector function. The unit tangent vector gives you the direction you're going, and then the differential ds is a little bit of piece of the curve. So you're getting force times distance. Well, as usual, if F is equal to mn, that's what we've been calling it, then the unit tangent vector we're going to let equal dx over ds, dx over ds, and then dy over ds. So here's our unit tangent vector times the ds. We can move the ds inside, and when we do, we get here, let's just go ahead and let me put this in. When I take this dot product, see if I move the ds in, that should be an s. When I move the ds in, it cancels all those ds's. So when I take the dot product, I just get an mdx plus an ndy as usual. And then when we apply Green's theorem to that, we get the normal form of Green's theorem. That's what we've been using in these examples. But now, if you go back and look, remember when we talked about the curl. Remember the curl is the cross product of the gradient operator, the del operator, and our vector function. Go back and look. When we did this in class, this was the third component, the k component. So one way to get this is to take that third component when you find the curl of this vector. Remember, we did this cross product in class. When I take the curl, when I do this cross product and dot it with k, I get this exactly. So see, one way we could write Green's theorem is to write it as the curl dot k and then the differential dA. This is just a 2D representation of what we're going to study in a few days called Stokes' theorem. Okay, or take it another way, say this another way. If we take this 2D expression and then extend it to 3 dimension, we get something what's called Stokes' theorem. And this is going to be the last thing we study this semester. So it's very cool. We can go from a line integral to Green's theorem to a special case of Stokes' theorem, and then that's going to justify looking at surface integrals, and then the final statement of Stokes' theorems be the last thing we do. One last thing I would like to do is this. Now, this is the second special case of Green's theorem, and what I've done, I've put this kind of in a picture. I stole this picture off the internet. Think of your vector field, and this is just an example. This could be any vector field. And what we'd like to see is how things are flowing through that boundary, how things are flowing across that boundary. Well, instead of like in the previous example, this one, instead of this one where we looked at the tangent vector, see, think of the tangent vector here around the boundary. It's kind of giving you an idea of circulation. Now, some books, some authors call this the circular or the circulation form of Green's theorem. And that's going to involve the curl, because curl tends to describe a rotation. This now, we want to look at Green's theorem in terms of a normal vector to the region or to the boundary. Now, remember in the previous example, or the previous discussion, we let the unit tangent vector be dx, ds, dy, ds. Well, here, the way we're going to represent the normal vector is we're going to swap these two and then make this one negative. Now, what we do know is that when we take the dot product of these, we should get 0. And we do, see? This would be dx dy, dx times dy over ds squared. And this would be minus dx dy over ds squared. 0. If the dot product is 0, we know that these two are perpendicular or orthogonal. Now, you might say, well, how did you come up with this? Well, look, I want you to look anywhere here, right here. How much is y changing? Hardly any, is it? Y is changing very little here. But now how about x? Well, x is changing. If you're going in the right direction, and this is the right direction, isn't it? If you're going in this direction, x is the only thing that's changing, but x is going in the negative x direction if we set up a coordinate system. So that's why we make that negative. Or another way to say it here, my pen would kind of be the tangent vector, and what we want to do, the negative is going to make us take a 90-degree rotation. Okay, so now, instead of looking at f dotted with TDS, we want to look at f dot, the normal vector. Well, again, if f has component form m and n, and now we put in the vector form for the normal vector, and we dot them, we get this. We get this here. Now, if we turn this around, now you might say, well, now, wait a minute. What's going on here? Remember, Green's theorem says whatever's in front of the dy term, we take the derivative of it with respect to x. It doesn't matter whether I call that m or q or r or w. It doesn't matter. Whatever this is, Green's theorem says we differentiate it with respect to the other variable. Now it's going to be minus, I want to differentiate this with respect to y. That should be a y. Okay, that should be a y. All right, and then that becomes, we have minus a minus, so that's the partial with respect to x plus the partial with respect to y. And if you look at that, that becomes the divergence of f. So this is sometimes called the flux form of Green's theorem. And what it gives you, what it's going to give you in this case, is it kind of measures the flow of the vector field across the boundary, or the flow through the boundary. And it's going to lead us to something, that's one of the couple of things we still have to study. It's going to lead us to the divergence theorem. And this is a special 2D case of this. We're actually going to study 3D objects in a vector field in 3 space, and we're going to see how the flow is either out or in for that object. And that's going to lead to something called Gauss's theorem that the double E majors love and adore. Okay. Hope this helps a little bit.